Hello and welcome to lecture 6. In this lecture, we will be focusing on another aspect of perturbation theory, and that is the degenerate perturbation theory. Remember, so far we were discussing time independent non-degenerate perturbation theory, where you had a single state which was non-degenerate, and on that non-degenerate state you were applying your perturbative methods, and you were calculating the correction to energy, correction to eigenstates, and so on. But if the spectrum of your unperturbed Hamiltonian H naught has degenerate states, then tracking down the evolution of these states as this perturbative parameter lambda becomes non-zero will present new challenges that we are going to look into this chapter, and we will first show that naive extrapolation of whatever we have learned in the previous chapter for a non-degenerate state will simply not work. We will also be able to appreciate the basic difficulty if we start with some example which we have already encountered on the very first day when we had looked at this two-state problem with the different energies, and then at the end we had put these two E1 and E2 to be equal. So the problem that I am talking about is this one. So on the very first day we had set one problem like this. We had a two-state system which was given by this matrix, and on top of this we had put a perturbation which was something like 0 1 1 0. We are going to discuss this problem, and by looking into this problem we will first try to understand where the problem lies if we simply try to use the non-degenerate perturbation theory results in figuring out the situation where degeneracies are there. Okay, so let's start. So as you remember, our total Hamiltonian H was a function of lambda, which consisted of the unperturbed Hamiltonian H naught and a perturbation H1. For H naught, we will choose the Hamiltonian for the two-state system as I just mentioned here, but we will choose these E1 and E2 to be equal, and we will just choose a number which we are choosing here as 1 to make our life as well as the calculations simpler. So for H naught we are choosing 1 0 0 1 to start with. What does it say? It is a Hamiltonian which is diagonal. So the diagonal elements are its eigenvalues. That means if we write H naught n naught equal to E n naught n naught, then these E n naughts are 1 and 1 respectively. Now let us apply a perturbation which we are denoting by 0 1 1 0. So this is the perturbation. So this is an off diagonal Hamiltonian. In fact, if you remember, this is basically one of the Pauli matrices. So we then have the total Hamiltonian H, which is a function of lambda, which is nothing but H naught plus lambda H1 as 1 lambda lambda 1. This is my total Hamiltonian. Now one can actually use the labels n equal to 1 and 2 The unperturbed eigenstates we can write down. So we use these labels n and n equal to 1 and 2. The unperturbed eigenstates you can easily calculate. I am not showing the calculation because this is just a 2 cross 2 matrix and you know how to figure out the eigenstates, and on top of that it's just a diagonal matrix, so it is even easier. So unperturbed eigenstates will be 1, and this 0 again here is telling us this is unperturbed. One of these will be 1 0, and the second eigenstate will be 0 1. And of course these unperturbed energies corresponding to these states will be E10 equal to E20 is equal to 1. So this is what is already known to you given this H naught. If you solve H naught, N naught and equal to E N naught, N naught, if you solve this equation, then this is the result that you are going to obtain. Now with the perturbation introduced to first order in lambda, the eigenvalues predicted from the non-degenerate perturbation theory, if you remember. So let us assume that non-degenerate perturbation theory still works. If we assume that, then what should be the first order correction to lambda? You know that this will be E1 lambda, which is E10 plus lambda, and then you have this H1 1/1th element, which is nothing but 1 plus lambda into 0, which is 1. Similarly, E2 lambda is nothing but E20 plus lambda H1, the perturbation matrix 2 element, which is again 0. So this is again 1. But of course the eigenvalues are unperturbed to first order in lambda since the matrix H1 is off diagonal. However, these answers are wrong that you have calculated using this. We can compute the exact eigenvalues of this matrix, full matrix H lambda, and you can see what are these eigenvalues. If you calculate the eigenvalues of this matrix capital H, there you will see that the eigenvalues of the full matrix H, these are nothing but 1 plus minus lambda. In fact, there is also a problem with the state corrections. If you remember, so let me write problem with state correction too. If you remember, the non-degenerate perturbation theory result will tell you that this is nothing but N0 plus lambda sum over k not equal to n H1 kn divided by En0 minus Ek0 ket K0. And immediately, because this En0 and Ek0, these are same, or E10 is equal to E20, these two are same, this implies that denominator is 0 and therefore we will be in trouble. So the question is, what can we do now? I hope you understood where the problem is. The problem is that if you try to imply, or if you try to apply the non-degenerate perturbation theory results to a problem where clearly this H0, the unperturbed Hamiltonian, has degeneracies, then it clearly shows that there is problem with energy correction as well as problem with state correction too. So, as I just mentioned, if you actually look at the problem very carefully, and if you are trying to figure out where the problem lies, then you will actually see that the problem lies in the eigenvectors. Why am I saying this? If you simply look at this matrix, the full perturbation matrix 1 lambda and lambda 1, this will give you the eigenvectors as 1 by root 2 1 1 and 1 by root 2 1 minus 1. No matter what are these values of lambda are, it does not depend on lambda. So the eigenvalues of the matrix H, which is representing the full Hamiltonian, are 1 plus lambda. Okay, let me write this also. 1 plus lambda, which I just mentioned, and 1 minus lambda. So these are the eigenvalues which depends on lambda, and these are the eigenvectors. But as you have seen that the formula to first order gave us nothing, no correction, and in fact you can try calculating the second order also and see if you can get any contribution or not. So you may, as I said, wonder that what actually happened, and as I just mentioned that the clue lies in the eigenvectors. So these 1 by square root 2 1 1 and 1 by square root 2 1 minus 1 are the eigenvectors of the full Hamiltonian, as well as they are the eigenvectors of the perturbating Hamiltonian too. So this perturbation, which we had written as 0 1 1 0, they also have the eigenvectors which is same as 1 by root 2 and 1 by root 2 1 minus 1. So these are the eigenvectors. On the other hand, for the unperturbed Hamiltonian H0, which I have just written here that the eigenvalues are 1 0 and 0 1. Therefore, you can note this strange thing that for the original Hamiltonian, we have 1 0 and 0 1 as the eigenvectors, and in fact lambda can be extremely small, extremely small, say 10 to the power minus 50 or 10 to the power minus 100 or 10 to the power minus 200, and already the eigenvectors basically change and becomes this 1 by root 2 1 1 and 1 by root 2 1 minus 1. However small your lambda is, you just add a perturbation which is extremely small and the eigenvectors change. What is the reason behind that? The reason behind this is lying in the fact that this object, these eigenvectors which I have written here corresponding to the original unperturbed states, they are not the only eigenvectors of the unperturbed matrix H naught. That is the important and most important point. Not the only eigenvectors of the unperturbed matrix H naught. Since the original matrix is degenerate, this 1 0 and 0 1 are just the two possible choices of eigenvectors, and certainly they are not the only choice or the unique choice. They are not the unique choice. In fact, any linear combination of 1 0 and 0 1 can also be an eigenvector of H naught. So that is important. So 1 0 and 0 1 are not the only unique choices of eigenvectors of H naught. Any linear combination of them can also be an eigenvector of H naught. And hence the space of eigenvectors of the unperturbed matrix H naught is the span of the two vectors that I have written here, 1 0 and 0 1. Therefore, it would be completely incorrect to tell that the eigenvectors before applying the perturbation was 1 0 and 0 1, and now after the perturbation they have become, or they have changed to 1 by root 1 1 and 1 by root 2 1 minus 1. That is not correct. Before applying the perturbation, you actually did not know what are the eigenvectors. They are completely ambiguous. There is no unique way to determine what these eigenvectors are. They can be 1 0 0 1, or they can be any linear combination of these 1 0 0 1. In fact, you have to recall that when we have a degenerate eigenstate, any superposition of these eigenstates will be a degenerate eigenstate. So this is what happens. In some sense, the eigenvectors of the perturbed Hamiltonian, which I wrote here as 1 by root 2 1 1 and 1 by root 2 1 minus 1, is one of the possible choices of a basis of eigenvectors for the original space. And what the perturbation does is to basically break the degeneracy. All those equivalent eigenvectors suddenly are not equivalent, and there are some preferred ones. Okay, so this is what exactly is happening. But so the fact is that the formulas for non-degenerate perturbation theory cannot be applied when we are dealing with the degenerate levels, and when particularly we are looking into applying the results of non-degenerate perturbation theory in a problem where there are degenerate levels and we are trying to apply that theory to the degenerate level itself, then it is a problem. So let us then actually try to formulate this thing, the formal setup, I should say, to study degenerate perturbation theory. So this is like a mandatory step to write every time. H lambda is H naught plus lambda H1. H naught is known, and it has some degenerate levels, and we also have this thing that E10 is less than E2 0 is less than E3 0, and in this way it reaches En 0, but then suddenly there are few states which are having the same energies. Suppose there are capital N number of such states, and in that case it should be small n plus capital N minus 1, and then we have En plus capital N, and so on, so on. So what does this mean? This means that we have capital N number of degenerate states, or capital N number of states which have same energy, and there are capital N number of energy eigenvalues which are having the same value of energy. So capital N energy eigenvalues all having same value, which we denote by, say, En0. That means you actually have a Hamiltonian whose diagonal entries are different, but as soon as it reaches this nth term or nth element, the diagonal entries are all equal. So it looks something like this, that you have this full Hamiltonian, and then you have these diagonal entries somewhere like this, and then it reaches the nth element, and then there are these capital N number of elements all in this capital N cross N box. So the dimension of this thing is N cross N. All these diagonal entries have the same value. These may have different values, these will have different values, but all these things, all these diagonal elements inside the box will have different values. That is, H naught is basically nothing but this diagonal E10, E20 like this, but then it reaches E small n0 and it goes till n such numbers, capital N numbers. So there are n such numbers which are same in this diagonal. And how do we actually denote these corresponding eigenstates? We will be denoting the corresponding eigenstates like this. We will denote them by n0 semicolon 1 ket, n0 semicolon 2 like this, n0 semicolon capital N. So this is up to capital N. So there are two labels that we are using to denote the degenerate states. So there are capital N number of states which are having the value of energy which is equal to En naught. This value is same for all these different states. So we are actually separating these states by these numbers 1, 2 up to n. All these states are going to form an orthonormal basis. That is important. All these states can form an orthonormal basis for a space which we denote by Vn. What is this Vn? The space spanned by the states n01, n02, n0n is termed as degenerate subspace and is denoted by Vn. So it's the degenerate subspace which is being formed by all these orthonormal basis vectors. This is the subspace of all states which are having the same energy E n naught. Hence, what we can immediately write is the following. We have H naught which is acting on n naught k and which gives us E n naught and the state back. This is your Schrodinger equation with k taking values from 1 up to capital N. Let us actually now start numbering these equations. Let us number this equation as 1. Let us number this equation as 2. And accordingly, we also know that this should hold that n naught p and n naught l should be orthonormal, delta pl. And let us call these as equation 3. Now let us remember at this stage, or let us actually comment at this stage, that this is not just something we are doing for the sake of calculations. Most of the problems that you face in quantum mechanics in real life will be dealing with degeneracies. So when you ask what happens to the first excited state of the hydrogen atom, you already have n square number of degeneracies, and first excited state means n equal to 2. So you have 4 different states which are basically having the same value of energy, and immediately you are stuck if you have not applied your degenerate perturbation theory onto these states. Now let us actually come back to the discussion and let us ask the question, what about the total state space of the theory? So the question is, we have just looked into the subspace Vn which is being constructed by choosing these orthonormal basis vectors, and these are all having the same values of energy. But of course we should ask this question, what about the total state space of the system? So that you can write it as curly h, denoted by curly h, which will be of course formed by Vn, but then you also have the rest of the states which are not degenerate, which we denote by V tilde, and this thing will be a direct sum of Vn and V tilde. This V tilde is spanned by those eigenstates of the unperturbed Hamiltonian H naught which are not in the degenerate subspace Vn. It is a direct sum. Of course, I am not going into the mathematical definition of a direct sum. We can discuss it later in the discussion part of these lectures. What is important is the fact that these Vn and V tilde are linearly independent subspaces. Okay, so let me first write about this V tilde. So this V tilde basically will be consisting of this span like this P0 kate, where P belongs to the numbers, some numbers Z. So this is what you are dealing with, the full space of the theory or full state space of the theory. And also I have just commented that V tilde and Vn are orthogonal. V tilde and Vn are orthogonal. That is also another important property. That means the inner product of any state outside the degenerate subspace with a state in the degenerate subspace is 0. What does it mean then? It simply means that first of all we will have P naught, Q naught, which belongs to V tilde. They are orthogonal and orthonormal. However, because V tilde is orthogonal to Vn, we will have this P naught, N naught, K equal to 0. So this is, let us call equation 4. So now with these constructs, let me just recapitulate a little bit what we have done. I have said that we have started with this perturbation equation, which is H lambda is H naught plus lambda H1. And then we said that we have this system where some states are non-degenerate, which are denoted with these things and this also. But then there are certain states which are giving me the same energy eigenvalues, and these same energy eigenvalues are being shown here. All of them have the same energy eigenvalues, and suppose there are capital N number of such states. Therefore, your H naught, which we are saying here, say, is a diagonal thing, E10, E20, E30. But then when we come to this nth element, we have capital N number of such values on the diagonal, which are all same. And correspondingly, we said that we will denote these degenerate states with the notation which I have shown here. Ket n naught comma 1, ket n naught comma 2, up to ket n naught comma n. And all these states can form orthonormal basis for these states Vn, or this V for this space Vn, which we call the degenerate subspace. The space which is spanned by these vectors, we call it, or we denote it by Vn, and we call it degenerate subspace. And these are the orthonormality conditions. And then we ask the question, okay, fine, I have a system, some part of which, some states in which are degenerate, but what about the rest of the state space? So for that we have introduced this V tilde space, which is spanned by those eigenstates of the unperturbed Hamiltonian, which are not explicitly in Vn. And we denote these states by these ket P naught or bra P naught or whatever. So this is what are the notation, and you note the notational differences here. There is of course clearly a notational difference in this whole discussion. We are denoting the space, the states which are not degenerate with just this single level P naught, but we are denoting the degenerate states with the two different levels n naught and 1, or n naught and 2, and n naught and n. That will make our life simple, as we will see soon. So let us frame the question now. We want to consider the evolution of the degenerate eigenstates as we turn on the perturbation by assuming that the states vary with lambda continuously. And as we already know how to expand, we will follow the same procedure and we will see what difficulties we get and where we get. So we will write this n naught k. We will start with this n naught k kate, and then we will apply a perturbation, and we will expect that there is a change in these states, and this change to some new state n comma k, and it varies continuously with lambda. So which we will always denote with this notation n semicolon k, which we write as or expand as n naught k plus lambda n1 k plus lambda square n2 k plus order lambda cube. Note that there is no change in the subscript here in k. I mean, like here when we expanded or here we had written down as n naught k, n1 k, n2 k. This k is just tells you that what are the number of states. So k will not have any subscripts. Now, in the same manner, we will also expand the energy. That means after we perturb, we will write this as enk lambda. I will just explain this notation here. That is also important why we are using two levels here. En0 plus lambda en k 1 plus lambda square e n k 2 plus order lambda cube, and of course there are other terms. Now this was the energy for every state of the degenerate subspace. To start with, this was the unperturbed energy for every state of the degenerate subspace. And you note that here we are using two levels, n and k. If I say only en lambda instead of en comma k lambda, I am already kind of making a mistake, because for each value of k, remember, if there are total capital N number of degeneracies, then small k can take values from 1 to n. Okay, so let me write here that these equations are holding for values of k running from 1 to n. So it is true for all these capital N number, from 1 to capital N number of cases. Now if I say that I don't want to write enk, rather I should simply write en lambda, then there will be a mistake, because for each value of k that is from 1 to capital N, the energy corrections might be different, and that is why energy corrections should carry this level k. So let me write it here. For each value of k that is from 1 to capital N, the energy corrections may be different, and that is the reason for keeping the label k in enk lambda. Now what do I mean by this statement? Again, if you actually go back to our discussion that we had earlier, that suppose I have this lambda along the x-axis and I am plotting this E lambda along the y-axis. And suppose now I have different states. Say I have at here one state which has no degeneracy. Then at this point of energy, suppose I have two states which are having degeneracies, that means which are having the same value of the energy. Then suppose here at this point I have say 4 states which are having the same values of energy. Now as and when I start, so we start from lambda equal to 0 and we go till lambda equal to 1 because that is the range. As and when I start applying the perturbation, I have seen that my E varies continuously with lambda. Therefore, I can have the variation of E like this from 0 to 1. But as soon as I apply here at this stage, which is doubly degenerate, there these two states can behave completely differently depending on lambda. So that's what I mean when I say that the energy corrections may be different for different values of k. So if they are, so here k is 2. So if there are k equal to 2, there can be k, here k is equal to 4. It may so happen that after applying the perturbation, the degeneracy is broken in the first order itself, and these E n k's become different values or different numbers for the same k. Because they become different numbers, then they are going to split the states, and we will call that the degeneracy is broken, or degeneracy is lifted, or degeneracy is removed. And we can calculate things easily if it is not resolved at the first order. If this degeneracy is not resolved at the first order, then it will make our life harder. But we will come to that in a later part. But for the time being, the reason for introducing this k is because that these energy corrections may be different for different values of k. Now let us also recall one thing from this non-degenerate perturbation theory. There we gave the argument that the first order correction to the state n1, that means, so let me write here again, recall that n1 correction or the first order correction did not have any component along n0 vector. In fact, we have seen that we can arrange this. So this was actually motivated from our observation in non-degenerate perturbation theory. So here also we will assume that n0k with npk will be 0 for p greater than or equal to 1. That is, in the expansion of the state that I have written here, look at this thing. This vector n1k does not have any component along n0k. Similarly, N2K does not have any component along N0K. So this is the assumption that we are making, and this is, as far as we know, is not affected by whether the state is degenerate and whether the state is not degenerate. It does not matter. So here also our assumption will be that N0K and NPK is equal to 0. But here comes the catch. NPK still can have a component along N0L with L not equal to K. So NPK can still have component in the degenerate subspace. This is very important to understand. We said that this NPK, P here denotes the correction, and since we have said that P is greater than equal to 1, that means this should start from the first order correction, and exactly the same thing that we have done in the case of unperturbed non-degenerate perturbation theory, that N0 N1 equal to 0, N0 N2 equal to 0. Here also this goes exactly in the same manner. But note this thing, that what happens if this K changes? That means NPK still can have a component along N0L. No one is actually stopping me from having a component along N0L. What do I mean by that? So by that I mean the following. Let us recall what are the elements of this subspace Vn. The subspace Vn had these elements N01, N02, N0K, N0 capital N. There were these n number of state vectors. Now may N1K, maybe N1K will not have any component along N0K, but it may still have components along N02, N01 or N0N. No one is stopping from having a component along these other vectors. So any NPK with P greater than or equal to 1, it not necessarily will have a component along N0K, but it may have components along other vectors like N01, N02 or N0N. So this makes life complicated, and that makes our physics as well as the arguments also much more non-trivial. So let us try to solve this problem by keeping all these basic things that I have introduced so far. So what is our problem now? The problem is that we need to solve this equation H lambda N K lambda. I am not going to use this subscript lambda from now on, just to remind you that there is a lambda dependence in the state also. N K lambda is the equation. This is the equation to be solved. So let us write this as H0 plus lambda H1, and this NK lambda, I know what it is. This is nothing but N0K plus lambda N1K plus lambda square N2K plus higher order terms. This is to be equated with ENK lambda. Also I am using that expansion, energy expansion, that is En0 plus lambda En comma K 1 plus lambda square En comma k 2 plus higher order terms into again the states n0k plus lambda n1k plus lambda square n2k like this. So all the arguments that we had given in the previous case of non-degenerate perturbation theory holds here also. We will just equate the powers of lambda, the coefficients of different powers of lambda, because this is going to give us a polynomial equation, and if the polynomial is going to be equated with 0, then each coefficient of different powers of lambda should be separately 0. Therefore, if we now look at the powers of lambda to the power 0 from this equation, you can see that this h naught acting on n naught k is going to give us en naught acting into n naught k. So this is the first equation and the most trivial equation, of course. N naught k is going to give me e, or let me write it the way we were writing in the previous discussion, minus en naught k equal to 0. So again, let me I probably forgot to number. What was the last number that I have used? 4. So this is going to, okay, what are the other equations here? Okay, 5, 6, 7, and then this is equation number 8. Now let us look at lambda to the power 1 order terms. So we have h naught into lambda and this n1k. So lambda to the power 1 term will be having h naught from the left hand side, and then there is this lambda enk1 acting on n1k. So that is the lambda order term, and there will be that is the lambda to the power 1 order term. But we will also have en naught acting on n1k. So this is going to give us h naught minus en naught n1k is equal to, now we have enk1 acting on n0k here, n0k here, and h1 acting on n0k here. The two order lambda terms are here. So this is enk1 minus h1 n naught k. So this is equation number 9, and of course up to lambda square, if I keep the terms, then if we may look at it carefully, so h naught acting on n2k is 1 lambda square order term, and then en naught into n2k, we can take this on the left hand side. So h naught minus en naught on n2k, and on the right hand side we will have enk1 acting on n1k, that is going to give 1 lambda square order term, enk1, okay, this is n1k, and then there will be one term which is from the left hand side, lambda h1 acting on lambda n1k. So h1 on n1k is another lambda square order term. So h1 n1k, and then we will have enk2 acting on n naught k, will give you the other lambda square order term. Let us call this equation number 10. Now these are, remember or note that the first one is trivially satisfied because that is the eigenvalue equation for the unperturbed state. Now these are the equation, all these lambda 0, lambda 1 and lambda square order terms, all these are equations for a fixed k. Every term in equations 8, 9 and 10 have the same k, but k can take values from 1 to capital N. And there are these three equations, therefore there is this 3n number of equations at your disposal. Now our experience with the non-degenerate perturbation theory will be helpful to some extent, although something will not exactly be the same. Energy corrections may not be hard at first order to calculate, but calculating the state correction, that means calculating this N1k, is going to be difficult. And you can calculate the state N1k in the part V tilde, but the part in the degenerate subspace Vn cannot be calculated from using equation 9 only. We will need equation 10 too. Maybe, we can discuss this later, but maybe not in this class, but we will see that. That is another important aspect. Now, we have figured out all the equations that are going to be required by us to solve for this non-degenerate perturbation theory case. So, we will discuss a solution to first order for the case in which the degeneracy in the degenerate subspace Vn is completely broken to the first order in perturbation theory. That is going to be our first assumption, that we are looking into a solution to first order for the case where the degeneracy is completely broken. It may so happen that at the first order the degeneracy is not fully broken. That is going to be difficult, but that case we will come later. That is the first order correction to the energies, split these capital N number of states completely to n different states. So what is the prescription that we are going to follow if we want to calculate the corresponding correction to energies and state vectors and all those things? So the first thing is that you have to hit the order lambda equation with bra n0l to understand that the H1 perturbation must be diagonal. First of all, this is one statement in the chosen basis for Vn, and also this will determine the first order energy shift or energy correction. That is the first step. What is the second step? Again, you can use this order lambda equation to calculate components of N1k in this V tilde. Remember, we just had said that, where did I say this? That, where it is? Here. We just said that this NPK with p greater than equal to 1, although by our assumption may not have any components along this n naught k, but it still does not prevent it from having components in other directions like n naught 1, n naught 2, or n naught capital N. That is one important aspect. So that we need to figure out. So this we are going to calculate by using the first order equation. And then you hit the order lambda square equation with n0L from the left side to determine second order correction. To energy ENK2 and the components of N1 semicolon K in the degenerate subspace. So these are the three steps that you need to follow in order to completely understand what is happening here. So let us actually, for today, let us actually look at this first part only, N0L H0 minus En0, this is the equation, N1K. So this is the order lambda equation, that is equation number 9 that I am taking, and I am applying from the left side by N0L. That's what I am doing here. So the right hand side, it is N0L ENK1 minus H1 N0K. And you immediately know that using equation 8, that H naught acting on N naught L is going to give you E N naught. So we will have E N naught minus E N naught acting on or multiplying N naught L and N1K. So this is going to give us, the left hand side is going to give us 0, and the right hand side is still N naught L E N comma K1 minus H1 N naught K. So our equation here now becomes little bit simpler, that N naught L, let us write it like this, take this H1 on the left hand side because the left hand side anyway is 0, N naught K equal to E N1 K, E N K 1 N naught L N naught K. Now we already know that what N naught K N naught L is. N naught K N naught L is nothing but delta LK. So this is going to give us delta LK. So we have our result, which is very important, N naught L H1 N naught K is equal to E N K 1 delta L K and this is for all values of L and K which belongs from or take numbers from 1 to capital N. This is our equation number 11. This is an amazingly beautiful equation because it tells us many important things about the system. If you want this equation up to the order lambda to hold, that means if you want equation 9 to hold, it is better be that H1 is diagonal in the basis that you are using here. That is the first point that this 11th equation is telling you, that if you want that order lambda equation to hold, it better be that H1, that is the perturbation matrix, be diagonal in the basis that we are using here. Hence, H1 is diagonal in the chosen basis of the subspace Vn. H1 may not be diagonal elsewhere on the full space, but on the degenerate subspace, it better be diagonal. So, if you want to work your perturbation theory ahead, work on the perturbation theory ahead, you cannot use an arbitrary basis of states. That is what this equation is telling you. It tells you that you have to start in the degenerate subspace that makes the perturbation H1 diagonal. In fact, that you have already seen in the first example of the two-state system that we have done. So, this equation therefore finally tells you that ENK1, the first order correction, because there is this delta LK, I will just replace L everywhere by K, is nothing but N naught K H1 N naught K. And let us denote this by H1, the matrix elements. We will use this NK notation. So this equation tells me two things. This 11th equation number 11 tells me two things. First thing is that H1 is diagonal in the basis that we are using here. H1 may not be diagonal elsewhere on the full space, but on the degenerate subspace, it better be diagonal. Why diagonal? Because there is this delta LK sitting there. It tells you that this cannot be, this has to be 0 if L is not equal to K. So that will give you this thing to be only the diagonal matrix elements. And secondly, it also tells you what is the correction to the energy, ENK1. The energy corrections are the diagonal elements of the matrix in the degenerate subspace. That is very important. And to this order, therefore, ENK lambda is equal to EN0 plus lambda H1 NK to the first order or to this order. You really have to start with the correct basis, the basis that makes H1 diagonal in the degenerate subspace. That is the first important point here. Now, life is simpler if the ENK1s are all different. So as you might be, so here are some remarks about this result. ENK1 are all different, that is, eigenvalues of H1 in the basis N naught comma K are all different. So this would have been the ideal. So this is kind of an ideal scenario. Not necessarily it happens every time. This statement that I have written here, it means that ENK1 is not equal to ENL1 with K not equal to L for all values of K and L taking between 1 to capital N. So now if the degeneracy is lifted, the basis states n naught k that makes H1 diagonal in the degenerate subspace are called good basis states. So that is something which is very interesting. If the degeneracy is lifted, the basis states n naught k that makes H1 diagonal in the degenerate subspace are or will be called good basis. So basically when you are doing degenerate perturbation theory, the thing that you look for is this good basis states. If the degeneracy is not lifted in the first order, it may be lifted in the second order in lambda. So that is where your life becomes a little bit more complex. If the degeneracy is not lifted in first order, it may be lifted in order lambda square. Finally, therefore, what you need to do is that you have to figure out a good basis set. Now, how can you find out a good basis set? Of course, you can actually do kind of take this H1 and you can explicitly diagonalize this H1 in a basis and you can see whether the basis is good or not. But of course, this is a very cumbersome process. You have to first select a basis and then you have to diagonalize and then you check that this is not diagonal in this basis. Therefore, you have to choose a different basis. So it's problem. So there is a theorem which tells you that if the basis vectors are eigenstates of a Hermitian operator, let us denote that operator by say omega, with all the different eigenvalues, and if omega commutes with the perturbing matrix H1, then the basis is good. Oh, that is something which is very surprising, isn't it? Because this will make your life easier, because sometimes we can assess without explicitly diagonalize H1 in a basis whether the said basis is good or not. And that is the way to check. You have to choose an operator omega which commutes with your perturbing Hamiltonian H1 and which has all the different eigenvalues. Then you can say that whatever basis you have chosen for omega should work for H1 and it is a good basis. So how to prove that? We will prove this and then stop. So let us assume that we have two eigenstates or the basis states in this degenerate subspace Vn, and these are say n naught comma p and n naught q with p not equal to q. Suppose eigenvalues of the operator omega are lambda p and lambda q, which are all different from each other. lambda q is not same as lambda p. Then what you get is this: you take this n naught p states and you try to evaluate your omega h1 commutator, the matrix element of that, in this basis. But because this omega always commutes with h1, this is 0, therefore this is 0. But you can still break this commutator bracket down and you can write it as omega h1 minus h1 omega on n naught q. And this is, you know, that this omega acting on n naught p is going to give you lambda p because omega is Hermitian. So this is n naught p h1 n naught q. And then minus minus this omega will operate on this n naught q and will give you lambda q n naught p h1 n naught q. And therefore this is nothing but lambda p minus lambda q n naught p h1 n naught q is taken common. But we have just claimed that lambda p is not equal to lambda q. And this implies that this object should not be 0 and the left hand side is a 0. Therefore, n naught p h1 n naught q must be 0. That is, non-diagonal matrix elements of h1 are all vanishing. Therefore, you have diagonalized your h1. Even without explicitly diagonalizing h1, you can comment that you have figured out this basis n naught p n naught q, which will make your Hamiltonian diagonal, perturbing Hamiltonian diagonal. You can always find an operator which is Hermitian and have different eigenvalues in the same basis. Many times this operator may be, for example, angular momentum, LZ, Z component of angular momentum, say LZ, for which all the states have different eigenvalues and it commutes with the perturbation, say. So one looks for such an operator that commutes with a perturbation for which your basis vectors may be the eigenstates. So that's what you are always looking for. So if you are figuring out a basis set which will make your Hamiltonian diagonal, then you are happy, because then this equation holds. This equation holds. This is very important. So let us stop here. We will actually discuss some examples tomorrow, and also we will continue to calculate the second order energy corrections and the state corrections also to first order.